Okay. Well, first of all, I would like to thank the organizer for inviting me to give a talk in this seminar. Well, I'll be talking about discrete exterior calculus. I'm going to give a brief introduction, and not only brief, I'll try to be brief, it would have to be a motivation. I'll try to motivate the concepts or the ideas why certain discretizations are made of geometrical objects. Let me mention discretization of partial differential equations. There are many methods: finite volume, finite element, finite differences. But this is another one. This is a novel one. Okay. By the way, what I'm going to talk about is the interpretations and implementations and examples that a group of people here in CIMAT, colleagues and students, we have been developing over the last year. People from applied mathematics, pure mathematics, and computer science. So it's a team with a variety of skills and knowledge, and there's a distribution of labor so that we can attack the problems from all different angles and see the results, test them. Okay, so as an introduction, let me tell you a little bit, very little bit of history. So discrete exterior calculus is a relatively new method for solving numerically partial differential equations. It was introduced around 2003-2005. It was introduced by Anil Hirani in his PhD thesis in Caltech, I believe, under the supervision of Gerald E. Marsden, the mathematician that we all know from the calculus and complex variable books, and many other things, also in mechanics. Now, the idea of discrete exterior calculus is to discretize exterior differential calculus, a theory that goes back to the end of the 1800s with Elie Cartan, and also to discretize all the concepts that appear from differential geometry. I will tell you that our approach, as I said before, is to understand. Well, our first goal was to understand what discrete exterior calculus was about. Once we understood it, we started testing it and comparing it. And then we also made conjectures as to how to modify it and to address problems or equations on domains that have not been, we believe, have not been dealt with. So I will motivate everything and test it. Discretizing the Poisson equation, the isotropic Poisson equation. Now, the hope about this method is that it will perform well, or maybe even better than some established methods in some circumstances. What are those circumstances that we still hope that might and has performed better? When the meshes that discretize the domain are coarse, they seem to perform better. This method performs a little better. Or maybe on curved domains. Like we have an example at the end of that. Also, I need to apologize if I make any omissions as to mentioning names, which I will not mention any other name from now on, and credit some possible result or interpretation to somebody, which I will not do. Because we have been doing it more or less from scratch ourselves as well. Now, I'll motivate discrete exterior calculus, which I'll call DEC from now on, in 2 dimensions. I will do it as simply as possible, and I will run the risk of making everything seem trivial. It is not trivial. Okay. So, first part of the motivation is in differential geometry, the Laplacian can be written or calculated as the composition of 2 operators in an alternate manner, which is called the differential operator, the differential, and then the Hodge-star operator, then the differential again, and then the Hodge-star operator. It is this that, or this position of two operators alternating, that we are going to try to discretize. Okay? So D is the exterior derivative, star is the hot star operator, and another ingredient that will be present in the philosophy of this method is Stokes' theorem, which in general reads like this. Omega could be a manifold with boundary of any dimension. Smooth manifold. Okay? Anyway, I will explain all of this in greater detail. So, before discretizing anything, I need to remind you or introduce you to the continuous setting concepts. I mean the exterior differential, the exterior derivative, and the hot star operator, and so on. So that's what I will do in the next few minutes, or next several minutes. Okay? So I will introduce the differential of a function to show you that you already know the exterior derivative in some way. The wedge product, which probably you don't know, or most people do not know. In computer science, they do not know the wedge product. The exterior differential operator, which is the exterior derivative, and the hot star. And then I will rewrite the Laplacian. So hopefully I will manage to do it quickly and clearly. Okay? So consider a function from the plane, or an open set from the plane to the real numbers, differentiable, and recall the definition of a directional derivative. The directional derivative of f at x0 in the direction of v is the limit of this Newton quotient. Okay? We all know that, we all believe it, that's the correct definition. The function is differentiable at every point if these limits exist at every point for every direction v. Okay? Now, I'd like to point out that, or remind you that the calculation of this number is linear on the vector v. Yeah? So I will abstract this notion of linearity by writing this. For each x0 on the domain, R2, I get a map. A map from R2 to R, in which for each vector I associate this number, which is calculated by that limit. Okay? It's a linear function. Okay? I will make another abstraction because I said I can do this for every x0 in the domain. Okay? So what I get is another map, df, which for every x0 gives me the linear map df to the x0. Okay? This df is already the differential, the exterior derivative of the function f. Okay? Let me give you a very simple example. I mean, this is when I run the risk of making everything seem trivial. Take the function g of xy to be equal to x. Take the first coordinate of the point. Compute the Newton quotient for that function, and the answer turns out to be the first coordinate of the vector. Okay? So instead of writing dg, I could write it dx, because essentially the function could have been called just x, and what we have computed is its differential. Okay? So what does this thing do, dx? Essentially, from this calculation we said on the previous slide, it asks every tangent vector, R2, give me, or not ask, commands every tangent vector, give me your first coordinate. A similar calculation will tell us about the function y and its differential dy, which will ask for the second coordinate of a vector. Okay? Now, in general, again, I will play with symbols, but to show you that you already know differential forms, I introduced already dx and dy. For a general function, again, we have the differential of f at x0 in the direction of v. Well, v, you can write it as the sum of two vectors, v1, 0, and 0, v1. Yeah, v2, sorry. Okay? So, as this operator df of x0 is linear, I separate it this way, yeah, on the 1, 0 vector, and I let the v1 out, the 0, 1 vector, and I let the v2 out. So that reads essentially as a third line, because those differentials in the direction 1, 0 is nothing but the partial derivative of f with respect to x. Similarly, for the other derivative, this is the partial derivative of f with respect to y. Anyway, once I've done that, I realized that v1 is the answer to the question, or to this command, dx of v. So I just rewrite it that way. This corresponds to v1, and this one corresponds to v2. Okay? So if I abstract or factor out or take out the v, what I have is the differential of f. The differential of f in standard coordinates is given by this partial derivative dx and partial derivative dx. You will say, but in calculus 3, I learned about the gradient. Okay, the gradient is related to this directional derivative, and we learned this in calculus 3, by this identity. It is a vector, so that using the dot product gives me the value of the directional derivative. Okay? So the claim here is, I reminded you that the directional derivative is defined just using a limit. Newton quotient, of course, limit. On this side, the gradient is a vector such that this identity is satisfied with respect to the dot product or the metric. So if we change the dot product or the inner product by a different inner product, that vector will change. So the gradient is dependent also on the metric. So the only point I'm trying to make here is that the truly essential or the truly original concept for the derivative is the differential, not the gradient. So we are going to work with differentials. Okay. We can have more general one forms using dx and dy and placing next to them more general functions, arbitrary functions. Okay? These differential one forms will also be related to vector fields by the same equation using the metric. Okay? So I do not want to offend the intellect of anybody, but this presentation is kind of tuned, taking into account that the audience might be very, very diverse. Okay. The wedge product. Let me tell you what the wedge product is, but I will do it with vectors and y vectors. Okay, we're already used to thinking of vectors as arrows placed in space and to associate to them algebraic objects and manipulate them. We are not so used to, or not used to at all, to associate algebraic objects to parallelograms, the locus generated by the combinations of a vector A and B. Also, one can associate an algebraic object to parallelepipeds generated by 3 vectors. Okay, those objects, for instance, for the parallelogram are denoted A wedge B. Wedge is the name we give to this little symbol that I'm going to highlight now. This little symbol, that's a wedge. Well, these bivectors and trivectors will live in new vector spaces, the vector space of bivectors and the vector space of trivectors, and so on. Now, one thing one notices straight away is that it is not the same to list the vector A and then the vector B. It is not the same as listing first the vector B and then the vector A, because the orientation that is determined by listing them one way or the other is opposite. That's a concept that we have all taken care of while studying calculus 4, or integration of functions of several variables. We have to take care of the orientation. So there is a difference in these two symbols, A wedge B and B wedge A. And it's captured by this minus, the difference in orientation. Okay? By this antisymmetry, or just think about deforming the vector A towards the vector B, you can see that when B approaches A, the parallelogram contains less and less area until the point on which, the two come together and you get a parallelogram with zero area. Actually, you only see a bit of a line. It's a parallelogram with zero area. So in the space of bivectors, it will be the zero bivector. Okay? Just for completeness, I will tell you that this product, the wedge product, is associative and distributive. So, just remember that the main property, really, the new property, is that it is antisymmetric, or anticommutative, if you want to call it that way. Now, with the one forms I told you about, dx and dy, they turn out to be the dual elements in terms of vector spaces of the vectors E1 and E2, because this one responds one to the question posed by dx, and also responds 0 to the question posed by dy, and the other way around with E2. So dx and dy are elements of the dual vector space of R2. We can define the wedge product, or think of the wedge product different ways. Define it in a similar way by the rules of anticommutativity and dx, dx wedge dx equals 0 follows from the first one. Or we can think of dx wedge dy as the dual element, of the square E1 wedge E2, which holds area 1. Okay? Okay, so now the operator B. I already showed you how to take the exterior derivative of a function. It was nothing more than taking the differential, taking partial derivatives, really. Now, if I have a general one form, like this one, which, as I mentioned, is related to a vector by a metric, we can define, or necessarily needs to be defined, this, the differential of such a one form, by this rule. Let's say, take the derivatives of the first function, wedge dx, because it accompanies dx, and take the differential of f2 wedge dy, because it accompanies dy. In that way, what we're going to get is this differential here, then the other one, then we distribute the wedge product, or the sum, but you realize that dx with dx will give 0, dy with dy will give 0, and here I will have dy wedge dx, which I have to change the order to dx dy, and a minus appears. So I get this expression. Okay? Now this expression is not totally arbitrary. This whole thing is motivated, is the necessary way of doing things because of Green's theorem, for instance. So the last identity, I have rewritten it here. The differential of a one form is this object. Now we call Green's theorem. Green's theorem of a vector field, for a vector field, reads as follows. The line integral of the vector field over C, which is the boundary of a domain, is equal to this object over the domain D. So it's relating a line integral with a double integral. Okay? Now notice that this object that we found by exterior differentiation is exactly the same as the one we have here. Okay? It is not coincidence. That's how the exterior derivative is going to work. So if I substitute this expression by the one we have here on the left, I didn't highlight there, this one, Green's theorem now reads like this. I have put the D and the curly D of border in red to highlight how there is an interplay here of an object being differentiated in some way and a domain and its boundary here. Okay? Let me just mention for completeness that Green's theorem, divergence theorem, Stokes theorem generalizes to any dimension on curved spaces or manifolds in the following way. Here the omega would be the f1 dx plus f2 dy, and the omega, the lowercase omega, and the capital omega would be the d. Okay. Now, that same equation I have just written, I'll express it explicitly how there is a relation between D and the boundary operator. So, if you consider the integration as a kind of a canonical pairing between objects, well, how do I do that? Just in notation. Substitute the integrals by these pointed brackets, pointed double brackets, in Green's theorem. Now it reads like this. Yeah, so it's a pairing of differential forms with domains, a pairing of two forms with the domain, and a one form with a curve. Okay? Very roughly speaking, this is not mathematically accurate. Very roughly speaking, what it is saying is that D seems to be the transpose of the boundary operator. And that is the first ingredient that we, philosophical ingredient, where we are going to take for discretization in discrete exterior calculus. Okay? Now, the hot star operator. Most people, except geometers, will be familiar with this, I suppose. So let me try to say it in as few words as I can. We have this little square formed by E1 and E2, the two canonical vectors, 1, 0, and 0, 1, and which has area 1. So the star operator in dimension 2 asks for the following. I give you, or says the following. Give me a vector and I will tell you another vector with which to make a square which is positively oriented. Okay? So, for a star V1, so which would be the vector that would give me another vector, which would be the vector that would make a square with E1 positively oriented? Well, it has to be E2, as I put in this drawing. Okay? In the drawing here, no, not highlighted. If I do it for E2, the vector that would complete the square, positively oriented, would have to be minus E1. You agree? Be pointing the way. Now, something a little less obvious, but let's say, if I ask you, what do I need to multiply E1 with E2? The square. What do I need to multiply it in order to get a square? Well, nothing. Well, essentially, you have to multiply it by 1. Yeah, but saying by nothing is not quite accurate. It has to be multiplied by 1, although you don't see it. And reciprocally, the star of 1 would be the square itself. Okay? Now, for differential forms, one can define it in various ways. Let's say we can do it by analogy. Like this dx asks for the length of the projection of a vector on the direction of the x-axis. So you say, well, which is the form that will complete this one to give me the area form dx dy in R2? But it has to be dy. what will complete dy in wedge product to give me again dx dy. It has to be minus dx. It's completely analogous. Okay? Okay. Hopefully that worked, that explanation worked. Dimension 2. Now I'm going to rewrite the Laplacian. And I will ask you, or I'll come back to these two tables, or basically to these identities here. I will come back to them perhaps several times. Take 2 seconds to look at them. Dx goes to dy goes to minus dx, okay? Because I'm going to use that. Come on. Okay, the Laplacian. Take a function from R to R, or an open set. The usual Laplacian, as we know it, is the sum of these two partial, second order partial derivatives. So what I will do is use my ingredients. I take the function, and I take the exterior derivative, is this expression as we already saw. Take the star of that. The star is applied to the differential one forms, i.e. is applied to dx and to dy. The star of dx is dy, the star of dy is minus dx. So I have this expression. Now, apply the exterior differential again, the one I explained you about. That means exterior differential of the first function, which is this, exterior differential of the second function, which is this, and you get this expression with second derivatives, dx and dy's. Correct? Now you realize dy with dy will give 0, dx with dx will give 0. All that remains are things that accompany dx dy, or dy dx with a minus. Dy dx with a minus is dx dy. Okay? So you get the Laplacian accompanied by this funny thing, area form. Well, how do I get rid of that? With the star operator, and I get the Laplacian. Okay? So with that, I have shown you that geometers, like any other mathematician, looks at an object and tries to deassemble it to see what are the ingredients. So we have separated the Laplacian in the ingredients. One is differential, which is defined with limits, and the other one is geometric, which is the one of the star operator. It measures lengths, it gives you right angles, so transformations by right angles and so on. Okay? So now we are ready for the discrete setting. However, nobody interrupted me for questions. Moderator? No? Nobody has any questions? I carry on then. So, in the discrete setting, the objects I will need to recall or define are the boundary operator on simplicial complexes, but in 2 dimensions. Then define the discrete derivative, show you the need for a dual mesh, a familiar concept in computer science, and then define the discrete Hodge star operator. Okay? So the boundary operator. So I want you to focus on the third line of this slide. We have a triangle with vertices B0, B1, and B2. In the slide, you will see that I put an arrow, kind of a circular-looking arrow, to show the orientation. So this orientation is encoded in the way I listed the vertices B0, B1, B2, first, second, and third. Okay? So, if I ask, what is the boundary of that triangle, or that simplex? And you will tell me, well, it is this side, and this side, and this side. Well, in mathematics, or in topology, we don't just list them. We actually write it this way. Formal sum, in which V1, V2 is listed as saying I am departing from V1 and arriving in V2, so I'm traveling in that direction, a direction which agrees with the orientation of the triangle. That means it gets a plus sign. However, look at V0, V2. I am listing coming out from V0, getting to V2. I'm traveling in that direction towards V2. That is the opposite way of traveling than the triangle is telling me, which is from V2 to V0. Okay? That's why it gets a minus. And so on and so forth. This philosophy applies to tetrahedra in the last line. It applies to one simplex and so on. Yeah? The boundary of an interval is the endpoint. From one you depart to the other one you arrive. One gets a plus and one gets a minus. Okay? Okay, so what is it? Now, consider a domain. So I made up this example, which will come up a bit later again, just to give you a sense of how to construct the matrices that will discretize these, the Laplacian. Okay, so consider this domain, this hexagon with 6 triangles, 7 vertices, okay, all oriented, very good. So what we're going to do is to each face, we are going to assign a coordinate vector. So we have 6 faces, we are going to have 6 coordinate vectors, right? Of our 6. We have 7 nodes, we are going to have 7 coordinate vectors, and out of 7. And in terms of edges, I have 12, similarly. Okay? Having done this, the boundary operator that I mentioned earlier becomes a matrix. Let me try to show you. If you take the face V0, V1, V6, and take the boundary, like what I explained earlier, you get this expression. Now, let's go back to the previous slide. So you have all these segments. These segments, or these edges, were assigned vectors, right? So one is the first, one is the second, and so on and so forth. So here, what we get is a plus, a minus, and a plus. Those coefficients are to be used as columns of the matrix that will discretize the boundary operator. And here you have a 1 and a 1 and a minus. This minus, for instance, belongs to this. Yeah, this one. And similarly for all the other faces. Okay? Now, for the edges, similarly, you have listed the edges here. Well, their boundaries are the vertices or nodes of the mesh. Okay? And here you see 1 plus and 1 minus. It corresponds to this 1 here and this minus. Okay? So we have a linear algebra expression for the boundary operator on a mesh, on a simplicial mesh. Okay? 2-dimensional. This generalizes to any dimension. The discrete differential. Remember, first, what I told you, that very roughly speaking, the boundary operator on domains is dual to the exterior differential by Stokes' theorem. We are going to use that. Now, how are we going to use it? The discretization of a function on a mesh is given by a set of values. The value, either known or unknown, of the function on each vertex, f of v0, f of v1, up to f of v6 in the example we have, which I will denote for short f0, f1, f2, and so on. So we have a column vector. Now, we already have a matrix for the boundary operator. We take the transpose, and that will be our differential. Okay? How do we apply it to, if we apply this matrix, or you multiply this matrix by the column vector of f, you get this answer of differences. So what are those differences? Let me tell you, they are very rough approximations, derivatives of the function along the edges. So each one of these entries is a value associated to an edge. Okay? They represent very rough derivatives. Now the question is, can we now write the Laplacian? No, not yet. We need the Hochstar. How do we go about the Hochstar? Well, so let's make some more drawings. So we are going to make drawings to generate a dual mesh. Well, let us see first. Let me remind you again, the Hochstar for E1 gives me E2 to make up a square, positively oriented square. Okay? Now, in our example of domain, the hexagon, take the edge B0, B6. What be the hot star of that segment? Well, give me the segment that will help me form a square, which is what I drew in the picture on the bottom right. Okay, so the segment is this blue segment. I hope you can see. It helps me construct a square. Okay, so that's the geometrical hot dual of the segment B0, B6. Now, why do we need to consider these segments? Okay, we have the segments of the original, or the edges of the original mesh. To those segments or edges, we got assigned these values, these rough derivatives. So those rough derivatives will be, well, like the one for here, a value assigned to this edge. However, many a time, we will need to know not just the directional derivative along a certain direction of the edge, but we also need to know what happens on the transversal direction. Let me say, for example, if you integrated a vector field along this edge, B0, B6, we still wouldn't have information about the work that is done in the transversal direction. So maybe it is useful to have a dual edge for time when I need to know what happens on the transversal direction. Okay? Now, so for each edge, now I have done this procedure. Give me or produce the segment that will help me form a square. So so I did it originally for B0, B6, and I put this blue segment. Now I did it for this one, and I get this segment here, and so on and so forth. I get this kind of hairy picture. Now, my domain is the hexagon, so you will notice first that these segments here are sticking out. These hairs are sticking out. They're not part of the domain. So, do I really want them? No, I don't want them. So, like a gardener, I chop them. Okay? Now I have these edges inside that are kind of crossing. They are meeting at a point, but they are going too far. What do I do to get a nice object like the one on the right, like this one? Yeah. Well, I scale them down. Okay. If I scale them down, then what I get is this cell complex. Okay, which looks nice. It also discretizes my domain, and it contains the information of the domain. Like the area of the whole domain can be computed, adding up the areas of all the cells, and so on. Okay. Now let me point out, dual mesh is a concept. A dual mesh is an object that is well known in other methods like finite volume, and is well known in computer science. So it seems natural that we should have this object in DEC as well. Okay. Now this object will help me accomplish the discretization of the hot star. In fact, I already did it. Let me remind you, the hot star, again, for a segment tells me how to complete it to a square, positively against the square. Okay? The scaling I just talked about earlier, at least for the inside or the inner lines here, the blue lines here, was accomplished by dividing by the length of the original edge. The original edge and the geometric hot dual have the same length. So what do? I scale it to measure 1, and then I multiply it by the length that I want it to be. The length I want it to be is this one. Or, well, that thing. Okay? B0, B6 star is the little dual edge of the dual mesh. I didn't write it here not to make it more crowded, but B0, B6 star is this segment, okay, in the dual mesh. So this rescaling is essentially, these two things. producing the complementary segment and scaling it down is essentially the discretization of the Hodge-Star operator. So the one we have focused our attention on is this one, the one easy to see. Edges. I have to send edges to edges, and how do I do it? Rescaling. However, this new mesh also gives me this relation. This cell, this hexagonal cell, is surrounding this vertex. What that means, and it's known in computer science, this hexagon, this blue hexagon, is the dual of the vertex. Now, for this vertex, for instance, the what do I call it? V3, the dual cell is this area here, made up by these two quadrilaterals. Well, that's irregular pentagon would be the dual cell, and so on. So the dual of a vertex is a cell, the dual of a cell is a vertex. That's all there is to it. So this is accomplished by this matrix. So for edges, I go from one to the other and rescale. Those are the entries of this matrix. And to go from vertices to the cells, the two-dimensional cells, I accomplish it with this matrix, the area of the corresponding cell in each diagonal edge. Okay? So the discretized Poisson equation now reads the following way. Here I have put a constant k, the diffusion constant, but just leave it aside. The Laplacian, the way I write it, and q. Well, for DEC is the discretization of the functions u and q, and then you have the matrices of the corresponding derivatives. I explained this one. I explained this matrix. I didn't explain this one because it would take me a lot longer, but it ends up being the transpose of this one, and this the inverse of the second Hodge-Star matrix I explained. Okay? So that's a discretization. Without many details, that's a discretization. So the matrix equation, now solve it, see what happens. See if you get a good approximation to the solution. Okay? So, but before I show you the numerical simulations, let me tell you, how we introduced a variation of DEC already. DEC with curved edges, curved boundary edges, based on the following two observations, and already in numerical simulations we have done. You see, the derivative, the discretization of the derivative, the information it contains is about connectivities of the mesh, and only that. Okay? The Hodge-Star matrices, what they contain are lengths and areas, the geometric part of the mesh. Okay? Now, what if I decide to have a circular domain instead of a hexagon, or the hexagon being the approximation to this disk? I decide to use the disk itself, and I mesh it this way with straight segments and some curved boundary edges. Now, the connectivities are the same. The lengths and the areas are different. Let's use those lengths, the true lengths of these curved segments and the true areas of these pizza slices. Put them in the Hodge-Star matrices instead of the rectilinear ones. Okay? That is CDEC, or the Discrete Exterior Calculus with curved boundary edges. So put it in and see if it works. Okay, so in one of the examples I'll show you, or several examples I'll show you, that it does work. Okay? So the numerical examples, I'll give you 7. So the first one, consider a disk of diameter, what is the diameter? Diameter 2. The heat diffusion constant, put it to 1. Okay? A source term equal to -1. Boundary condition 10. So it's cold in the middle. Just on the boundary you have the boundary condition. You have an analytical answer to this problem to compare with. And we propose some meshes, okay? Like this one and this one, they are quite coarse, okay? They're not fine meshes. And what do? Well, we solve the system for those measures. We set it up as many triangles as needed, and so on, and solve the system. What we found out in this example is that the maximum temperature value, comparing it with finite element method with linear interpolation functions, is that DEC finds the correct value from the beginning with the coarse meshes, while finite element struggles a bit. You have to refine. It works. Finite element works. And there's no question about it. So it's one very well-established method. We are comparing it. Actually, comparing with other methods is something that we haven't seen widely in the literature. But we are doing it here. So now these graphs, or these pictures you have at the bottom, you might not be familiar, they are contour graphs in which the value of the function is given or represented by the color given by the scale, going from 10 to 1025. Okay? Now, this other contour graph is the magnitude of the gradient vector field, which is another measure computer scientists and engineers like to see if it's actually working. And it works out exactly the same as finite element method. Okay? Now this is the interesting graph with the very first coarse mesh. I don't know if you can see the detail. Probably not. I mean, close to the computer maybe. So finite element is the pink or magenta dotted line, and DEC is the dotted green line, And so you can see that with respect to the true solution, DEC is hitting the graph straight away, while FEM in the first mesh and the second mesh is still close, but it is not quite there. Okay? This is one of the properties that is expected that DEC will have throughout. It respects the geometry of the problem, the physics of the problem, so it will hit the solution sooner, sort of. These are kind of cross sections of the graphs, the corresponding graphs, along a diameter. Okay. Now the other example, we chose another domain, looks like a bell head, sort of thing, with curved edge, a curved boundary, to use DEC and FEM and CDEC, the one with curved boundary edges. So what we see, if we focus on these columns, is that DEC, doesn't let me, but this column here, and the temperature, DEC is behaving quite well, even in coarse measures, but CDEC behaves even better. Yeah? It behaves even better. Okay? Then we have, well, the cross-section graphs doesn't, I mean, the difference between the methods is very little, so you cannot see difference in these graphs. Then we took another one in which we consider heterogeneity of the domain. We have two materials, one for most of the square and another one in the disk in the middle, okay, with the different boundary diffusion constants and boundary constants. Okay? So we said the three methods to work in some meshes, and this is what we get. And again, we see that CDEC, not so much DEC, but CDEC is doing quite well, the one here in the middle. Okay, so that's quite encouraging. It is fulfilling its promise. Not the original DEC, but a variation of it. Okay? These are the cross-section graphs, and you see that CDEC, which is the red one, is hitting the correct values. DEC and FEM are kind of struggling for second and third place. CDEC is winning. Okay? Another example. We were wondering, Owen, you might be wondering, in the mesh that I produce, essentially the new nodes of the dual mesh are circumcenters, and I join them by straight lines. Is there no chance of moving that meeting point, instead of being the circumcenter, being the incenter, the barycenter, or an arbitrary point, and joining them, those dual points, by curved edges? So this is what this graph shows here, a mesh which we have a simplicity complex. We have not considered circumcenter, we are considering probably the incenter or something. And the red segments were not chosen arbitrarily. We were thinking, well, what do straight lines do? Straight lines do minimize length. And here we have, if we have 2 points, 2 of these incenters, for instance, so on this one and this one, for instance, well, the ones that I'm pointing out with the mouse, what would be the reasonable minimizing curve that will join them? Well, what did the other dual segment do? The dual segments cross the original edges orthogonally and minimize length. So what we did was to set up a variational problem for curves to minimize length and cross orthogonally the original edges. The problem does actually have an analytical solution by sine, cosine, by trigonometric function and a linear function, and they come up to be these curves. They are minimizing, they cross orthogonally, and the curvature is bounded. There is a reason to bound curvature that I might tell you if you want to know. Okay, so we run the experiments, meshes, the discretization with the corresponding lengths of these things, areas of the dual cells or whoever it was involved, and these are the cross sections of the solutions. They don't look bad in the contour graphs. They do converge again, but in the cross section graphs you see that the first approximation is actually quite poor. I mean, the one that has fewer edges, fewer points, and it is not as good as DEC and CDEC. So numerically, it converges. One can probably prove that this variational approach converges, but what it shows is that the circumcenter is actually optimal. Okay. The fifth example, which we believe nobody has done either, is work the Poisson equation on a surface, a curved surface. So we took the sphere because it's the easiest, we think, curved surface. We set up the same problem and solved it with there are 3 columns here at the bottom. Let me see if it lets me highlight them. These 3 the last 3 columns here. So there is the first one of those 3 columns, last 3 columns, is spherical deck. The second one is flat or rectilinear deck, and then finite element. The spherical one, what does it take into account? Well, you take a mesh whose segments are not rectilinear, are curved. They are lying on the surface of the sphere, and you are considering the lengths of those segments and the areas of those curved triangles directly on the sphere. So we put it in the scheme, and it works better than finite element with linear interpolation functions. So the moral of the story so far is that if one considers the geometrical objects closer, or the actual areas and lengths of the domain that you are considering, not an approximate simplicial complex, rectilinear simplicial complex, the approximation works better. Okay? Then another one. We decided to attack another problem that apparently has not been solved, which is how to solve the anisotropic Poisson equation with discrete exterior calculus. So we did it, and we found out how to do it, and the simulations come out like this. It is in in the magnitude of the gradient vectors that the actual anisotropy is shown. So, for instance, here we have that the diffusion tensor has two different eigenvalues. It's rotated by 30 degrees. So here you see that it behaves differently in two directions, 30 degrees rotation. Okay, so that was quite satisfactory. Okay, and then a last one. What does it say? Close. Here I will have to switch to another file. Come on. Huh? Why don't you want to do it? It's a stock. Oh, what do I do? Okay, this one. Okay, let's see. Okay. What is this? Is the dynamic problem of heat diffusion. So it's the Laplace equation with time dependence, and we set it to work, and the final answer is pretty much the same as the one of stationary problem. Okay, so we have pushed deck to be in, to work in the stationary and in the dynamic setting. Okay, now let me close this. That's another thing we've done. No, let's see the next one. Okay, so finally, just some remarks. So let me start by the number 5. So we have been working in 2D to understand it, implement it, test it. We have developed some variations of it, a variational that didn't work so well, anisotropy, which worked resolve, spherical, transient, or dynamic, and we have also developed a local formulation, which is important for people in numerical methods. That means it's working out, making the triangle by triangle, and then assembling a big system whose profile is very sparse and easy to solve. So the computational cost is similar to finite element and so on. In terms of future work, we want to work with other equations like Darcy's equation, and we want to go to 3D and work with elasticity and many other things. Okay, so now one last thing to point out is that this thing can be applied not just to functions. It can be applied to differential one forms. Let me put it this way. In elasticity, many times people want to compute the stresses of the material along the edges of the discretization, along the edges of the mesh. But the equations are set up that are solved for another function, a primary function. So the idea would be, or what we are after is setting up the equations on the edges and solve the system on edges instead of on vertices. That's a novel concept for people that work in finite volume and so on and so forth. One equation in which that has been done already is for Darcy's flow equation, where what you want to solve for is a vector field. The vector field is dualized to a one form, a differential one form, and a certain equation is set up and solved. Okay? Okay. So there are other things that I already mentioned. I just listed them down in case I have forgotten something, but I think I haven't. And in terms of references, I'll give you very, very few. The original work, is in Hirani's thesis, but in terms of an article, is in this article by Hirani, Maas, and Desbrun, and Delk from 2005. The notes that were most useful to learn in the first instance this method was the notes of Andrew Gillette, also available online. And most of what I've said here and more things are contained in this paper that we wrote recently with 2 colleagues and 1 student who implemented the first versions of Discrete Exterior Calculus. Okay. So I think that's all, and I'd like to thank you for your attention.
Okay, Rafael Herrera, he is one of the researchers here at CIMAD. We thank you very much for this talk. Do you have any questions at the room or in some part of the world?
I have a question. Do you hear me?
Yeah, I can hear you.
Yeah, so in your future work, you mentioned other equations. By the way, I'm Gerardo Hernandez. So do you expect to formulate equations like shallow water or Navier-Stokes in manifolds like the sphere, where the formulation is independent of the choice of coordinates?
Yes, I mean, what we will attempt is to formulate, to discretize any equation on any domain. We started with this one, the Laplace equation, because it's the simplest one. But we are going to, we are going to move on to more complex ones, more difficult ones. And now I would like to point out that although it is the simplest one, understanding how the discretization works thoroughly, what has meant is that we have been able to propose variations that actually work better than the original scheme, so that we carry all this knowledge to the more complex equations in order to deal with the problems that might arise in dealing with those equations, like numerical instability and things like that, or the approximation not being quite right. I mean, the principle of this method is that it respects, in principle, the geometry of the domains in a more faithful way. Okay? So we expect to go to all the other questions. Yes, Miguel Ángel Moreles wants to do the shallow water, Botello wants to do the Navier-Stokes, and so on and so forth. Well, we are kind of giving one step at a time, because our philosophy is not just to do it theoretically, just do this and so on. No, we propose an idea, we implement it and see if it works. If it works nicely, if it will carry on forward, or it should be discarded, sort of thing. Yeah? So, did I answer your question?
Yes, thank you.
Okay.
Any other question?
Have you looked yet at how it compares to the FEC, the Finite Element Exterior Calculus?
So we haven't compared to the finite element.
Repeat the question. Please repeat the question.
Have you looked at how it compares to the Finite Element Exterior Calculus?
The question refers to another method developed by Douglas Arnold and collaborators of his, which is called Finite Element Exterior Calculus. I think, or I speculate, is kind of a hybrid method between finite element and exterior calculus. However, well, the answer is no, we haven't compared it. And actually, we are not aware of any open source code that will allow us to run simulations side by side. If you do know, or you come across any code that could allow us to do it, we will try to compare it. I mean, we do believe that in order to improve the accuracy of this method, which as I say is a relatively new method, in order to improve it, it will have to be hybridized with other ideas of other methods, yeah, to increase the order of approximation. Okay, what do I mean by order of approximation? You might have noticed that I said finite element method with linear interpolation functions every time I mention finite element method. Well, it's because finite elements can use quadratic interpolation functions, cubic, or whatever you want. Now, when comparing to quadratic, the discrete exterior calculus is behind. Yeah? But quadratic finite element method needs more nodes on the mesh. And so, in a way, it's a give and take between greater accuracy or greater order and size of the calculation, size of the matrix equation you have to solve at the end. Okay? Okay, I hope I answered your question and I said a few more details.
Any other question? Okay, so we thanks very much, Rafael Herrera from CIMAT. This is a wonderful talk. Thank you very much, and bye-bye to all till the next time. Bye.